Let's look at topic 4, which has to do with trying to find approximately how far stars are away by using no telescopes whatsoever. So let's deal with a couple astronomical units. One is light years, which is pretty easy to understand. A light year is simply the distance that light would travel in a year. And the other is an AU, which is an astronomical unit. And an astronomical unit is the distance from the Earth to the Sun. And so there are 2 points along Earth's elliptical orbit that it is about 1 AU away, and that is summer solstice and winter solstice. The Earth is about farthest away from the Sun, and we call that 1 AU, or astronomical unit. The term parallax is going to be important here because this is a technique that we use to help give an approximate distance as to how far the Sun is away. And so when the Earth is from this distance, 1 AU, which is in its elliptical orbit, the farthest away in July, summer solstice, and then this distance in its elliptical orbit, which is in December 21st, so the winter solstice, we can draw a straight line across it to make a base, and then we can create a triangle, and we can start to use geometry to help us solve how far away approximately the Sun is. We draw a straight line. Whoops, let's use a different color. We can draw a straight line here, make a right triangle, and solve it. So let's get into that technique that I'm using here. It's called triangulation. So the longer we can create our baseline to use triangulation, the better. So here's a point of a distant object. In this picture, they're saying, let's pretend it's a tree. And we can't actually walk across with a meter stick to tell how far the tree is. Well, we can use a protractor here, and we can measure this baseline. And so if we have this angle, and we have this angle, and we have this baseline, then that will give us, we can measure this unknown distance here. And so let's do that, and I'll show you how this technique, triangulation, works. Besides triangulation, we could also use trigonometry or trigonometric functions, but instead what we're going to do is for now use triangulation. So let's say two students, need to know how far the tree is away from them. So they separate themselves 10.6 meters away, and they take their protractor at here and they make an angle of 76 degrees and then an angle of 76 degrees here. That's enough information to help us find this distance A, from the baseline to the tree. So how's this done? Well, it's done by using a technique where we make a scale drawing on paper. And so I'm going to take 10.6 and I'm going to scale it down. And on paper, with my ruler, I'm going to make my scale baseline. And I'm going to make it 10.6 centimeters exactly with my ruler. Then, here's my tree. I'm going to take my protractor and I'm going to draw a line that goes 76 degrees from this baseline, and I extend it as far as I can. Then I take my second line, and with my protractor I go as long as I can, but I make sure this is 63 degrees here, like in the real drawing. So 76 and 63. Now, in my scale drawing, I can take my ruler, and wherever these lines intersect, that's where the tree is. And with my ruler, I measure the distance that it is from this intersection to the baseline such that it makes a right angle. And I find out that that is, on my ruler, that's 14 centimeters. Now, once I have that in my scale drawing, I can jump back to real life. So when I did my scale drawing, the baseline, what did I do? I converted it to centimeters. And so if I take 14 centimeters, I convert it back to meters, then in real life, it would be 14 meters because my scale is 1 centimeter is equal to 1 meter in real life. Let's try this again. So here's the real object. Here's the target. And so I set up outside, I set up two angles, 65 and 75. I make sure I measure my baseline. And so my baseline is 20 meters. And I take this in real life and I make a scale drawing of it. And so in my scale drawing, maybe I make this so many centimeters. And I take my ruler and I make sure that I extend a line that's 75 degrees. And I extend another line that's 65, and wherever it crosses is the target. I take my ruler and I measure the distance here, whatever that may be. So they're saying here, let's make our baseline 6 centimeters. So let's say this is 6 centimeters. And they're saying in real life, 1 centimeter is equal to 20 meters. So if this is 6 centimeters, then the real baseline, of course, is times by 20 meters. It would be 120 meters. So we measure this, and this is 8 centimeters on our scale drawing. You got to put your ruler down to do that. We've got to convert that now to real life. Okay, 1 centimeter is the same as 20 meters. So if we have 6 centimeters, that's how many? So times by 6 times, or 8, sorry, 8. We have 8 centimeters because this is 8. So from here to here times by 8, from here to here times by 8, it would be 160 meters. The distance from here to our real point along here would be 160 meters. Let's try one more. Let's say the tree is a certain distance away, but we don't know how far the tree is away. We're trying to find that out. So again, in real life, we've taken, that's a little curvy, sorry. We've taken a protractor outside and we've made an angle of 85 and we've made another angle of 82 and our baseline is 85.6. So let's scale it down. And let's make this 8.56, so every 1 centimeter is 10 meters in real life. Okay, and let's make sure when we draw this out, that's 85 with our protractor right there. And let's make this 82 with our protractor. So all we need to do now, once we've set our protractor, extend the line wherever they cross, right there if I'm neater. Then I draw a line straight down and I measure this line right here, whatever it may be. And let's say it turns out to be exactly 10 centimeters. So then what would that be in real life? Well, for every 1 centimeter it's 10 meters. So if this is 10 centimeters, this distance would be 100 meters in real life. It's important to note that we can calculate something called percentage error. So if we do that, then we can get an idea as to how far you need to make your baseline. Just to let you know right ahead of time, the farther this baseline is, the more accurate our real result will be. So if these two people, A and B, are close together, which means a small baseline, then how accurate our calculation is compared to if we actually really measured it would be not as good. But if you make a really long baseline, then your results are going to be more accurate. So let's say our baseline is only 10 meters apart, angle A and angle B, and calculated, our percentage error is going to be quite high, maybe somewhere around 40%. But let's extend the baseline longer and make it 20. Now our percentage error is going to be only about 30, and if we make an even longer baseline, our percentage error is going to go down to about 10%. And so in general, this technique that I'm using, triangulation, helps us give approximate distances between two stars using this technique. So how far would it be from here to the closest star? Well, we take a baseline as long as possible, which is usually the Earth's position in the summer and then the Earth's position in winter, and we have to compare these angles to calculate this distance, usually in astronomical units or AU, because meters would be too big a number. So hopefully that gives you an idea of how to use this technique.